So what's happening here? I have a small electric motor of the type on scitoys.com. It consists of a coil of wire with some special insulation, which we'll talk about in a little while. A magnet, it's in that bundle of masking tape, and a DC current caused by a 9-volt battery, which is here 6 D cells. And as you can see, all of that alone is enough to keep the coil of wire spinning. So I'm going to stop it, and we'll discuss what's going on here. So I disconnected the battery. And as you've learned from the discussion of forces on charged particles, the force on a charged particle moving in a magnetic field is perpendicular to both the field and the motion. So we can tell from the motion of the loops of wire that there must be a force on this bottom rung actually towards the camera and one on this top rung away from the camera, because that's what makes the thing spin. So here's our diagram of that. Got all the essential components we've talked about. We have our magnetic field caused by the magnet in orange, that's B. We have the forces I mentioned, bottom one coming out towards you, the top one going away. And you can see that if you were holding your hand on that coil of wire and pulled them in the direction of those forces, you'd put a torque, you'd cause it to spin. I also have the current labeled, and let's talk about how the current is the motion of charged particles. If you think back to the discussion of charged particles and the force they experience in a magnetic field, this charged particle, this positive, was me. I was running across a magnetic field that was coming towards the camera, and my perpendicular motion to it, according to the right-hand rule, caused a downward force. When I went the other direction, my perpendicular motion in the magnetic field caused an upward force. The same thing happens in a coil of wire. Based on a diagram in a textbook, which I'll give in the notes to this video, I made this into a square. I thought they had a good idea there, because it makes it easier to see. Electrons are what's moving through wires. They first started studying electricity and magnetism before anyone knew what an electron was. So they wrote currents as being a series of positive charges moving through wires. It's a little bit weird since we know they're actually negative, but it works the same. It doesn't really make a difference. So we'll pretend there's positive charges going through this wire, and it doesn't matter if that positive charge is in the wire versus in the air. It's still cutting across a magnetic field just like I did. So on this loop of wire, the right-hand rule says that charge is going to have an upward force on it. And remember, there's trillions and trillions and trillions of charges doing this, and they all have an upward force on them. That tends to pull this wire up. On the other side of the loop, it's going the opposite direction. So just like I had opposite force on me when I switched directions, these ones will have opposite forces. So that pushes this wire down. And between that push up on the left and pull down on the right, that causes a torque and it causes the thing to spin. The parts that are in the same dimension as the magnetic field, so here and here, there's no force, so they don't contribute. So that is what makes the thing start to spin. So there's one final issue with the motor. If the coil is set up at first so that the current is going in a clockwise direction like this, so the right up top and the left on the bottom, it's not going to stay like that. As the bottom comes towards me and the top goes away from me, it's going to flip. This bottom piece will move up and become the top piece, resulting in on top the current will go the other way. That will reverse the force too. And what's going to happen is as the thing rotates, the two situations are just going to go back and forth with the force constantly reversing. Let's see what that looks like. It's definitely a magnetic force. It definitely started going, but it's like it's rocking itself back and forth. First it goes one way, then it goes the other way. It doesn't really lead to any sort of net motion. It's almost like the forces are opposing each other. They pull one way, then they pull the other, then back and forth, and nothing happens. So this diagram shows pretty much what we had before. We have the current going clockwise around the loop, putting an inward force up here and an outward force down here. That's going to make the thing rotate. But as we said, when it rotates 180 degrees, the current now is actually flowing the other way. And that means the forces are in opposite directions. So here we're making this thing rotate in one direction. Here we're making it rotate in another. Those two are going to fight each other. And that's why we saw it rocking. What we need to do is we need to turn off one of these two situations so that it doesn't actually get to cancel out the other one. Let's see how we do that. We'll look a little bit closer at the mechanics of one of these motors. The support base is just wires, and that's where the electricity comes from. One side's hooked up to positive, one side's hooked up to negative. It's a DC current. It always goes in one direction. We assume the current comes from the positive and goes to the negative. The thing that rotates looks like a bare coil of wire, but it's not. It's called magnet wire, and it's painted with an insulator. So although these coils look like they're touching each other, it actually has to go through one after another, and then it's basically just one long piece. If you want electricity to actually flow in or out of the coil, you have to scrape off some of the insulation using a knife. Let's see what that looks like for the motor we've already built that didn't work so well. That motor is one where I scraped the insulation off of all sides. It's definitely a magnetic force. It definitely started going, but it's like it's rocking itself back and forth. Now this rocking isn't because the current reverses itself. This isn't actually getting high enough for the coil to flip and let the current go in the other direction. The battery's just not giving it enough energy for it to even get up there. We'll see on the motors that work that if they don't get a kick to start them and give them the inertia to coast, they'll rock back and forth too. But the problem with this one is even if we gave it a kick, the current would reverse and it would go backwards. Let's look at a motor that does work. Remember, we have to find some way to turn it off for half its cycle so that it doesn't get pushed back the other way. If we spin the motor, you can see that half of the enamel's been rubbed away, but the other half is still there. And that means that when the motor's like this, the copper wires are touching and electricity's flowing. But it's when it's like this, the supports are touching the paint and electricity's not flowing. So in this state, it's actually turned off. But when I flip it over, it turns on. So our motor's only on for half the time. When I give the loop of wire a little kick, it keeps going. And it's actually acting as a tiny little electric motor. The chemical energy of the battery is being converted into kinetic energy. So we can see it works if we just eliminate one of these two situations. If we just turn the motor off when it would be like this. And then it gets its push when the current is clockwise. It then switches off and coasts through the other half of its cycle and then gets a push every half cycle. It's not the most powerful way to build a motor. A much better way would be if we could switch the direction of current as the thing rotated. Let's look at a motor that can do that. So I have another motor here, and this is called a St. Louis motor, and it's a really good model for all practical DC motors. So this is a model for how the fan in your laptop works, or how a motor in a remote control car, or really any battery-powered motor does its job. I'm going to stop it from spinning, and we'll take a look at what the pieces are. So first of all, there's this tan coil of wire, and that's an electromagnet, and these compasses tell us about the direction of the magnetic field. It's apparently coming out of this end, looping around, and then pointing back in here. So by symmetry arguments, we can assume it's doing the same through the spinning part of the motor, and the magnetic field is pointing in the direction I'm pointing away from the camera. So remember, the problem with DC motors is the current never switches direction. So if I was going to do the right-hand rule in this case, for argument's sake, let's say the left side of that green coil, the current is heading upwards. The imaginary positive charges are pointing towards the ceiling. In other words, it's rotating clockwise from our perspective. Let's do the right-hand rule and see what happens. So we know the magnetic field is pointing in the direction of my bottom fingers from the compasses. So we'll point it that way, and we'll know that from the argument that the current is heading clockwise, that the positive charges are heading towards the ceiling, like my index finger says. What that means is we should get a force on the coil of wire in the direction of my thumb, towards the left. So that's going to pull the coil towards the left. And because of the way it's wired, the other side is actually going to be pushed away. Well, that's great until it turns 90 degrees. Then the opposite arguments are going to apply, and it's going to get pushed back the other way. And it wouldn't go anywhere. It would just get pushed back and forth. So in the simpler motor you saw, the one from SciToys, we solved this problem by just having the motor be off half the time. The rotating part only made contact with its power supply 50% of the time because I only scratched off the insulation on half the wire. This has a much more ingenious solution. I don't know if you can see it, but that piece of metal is broken in the middle. It's broken on the other side too. And these things that are touching the spinning part, these brushes, they're what are actually hooked up to the power. And they alternately touch one side of this metal spinning jacket or the other. And what that means is it's constantly switching back and forth, whether positive or negative is touching each side of the jacket. And that means the coil is reversing the direction of its current, just as if it was alternating current. And that means that we're always getting pushed in the right direction because the time after we've gone around once, it flips, current reverses, so now it continues to push in the direction we want. So it's on all the time instead of half the time, like the previous motor. With an AC motor, you don't have to because the current automatically reverses, so an AC motor is much simpler. But there's lots of applications where we need a battery, which is portable, to power an electric motor, and this is how it works. Not surprisingly, this brush mechanism can wear out after time, and that's why DC motors eventually have to be replaced.